The biggest factor which will affect how much carbon is present in different soils is the depth of the soil. Probably pretty obvious, but deeper soils have more carbon because there is more soil. But the amount of carbon isn't actually the same all the way through the depth. We can use secondary data from Bradley and colleagues who carried out research into the amount of soil in different types of land use across the UK. They came up with averages which allow us to estimate how much carbon is present in each land use if we know the depth of the soil. So all we need to record is the land use type, and the categories they used were woodland, arable, pasture, and semi-natural, which is unmanaged land, such as this here. And we need to know the depth of the soil. So far, we've discussed the concept of sampling strategies, but we haven't shown any. This time, I'd like you to discuss, in this open cell side here, how we would find the average soil depth across the land. What should my sampling strategy be, and how should I carry it out? Hopefully you decided that since I want to know the average for the whole area, I should use a random strategy. So to do that, I can set out two tape measures. One is an x-axis, the other is a y, and that creates me an invisible grid coordinate system. I'll then use random numbers to decide my location. I've got a random number generator on my phone, and I want my numbers to be between 1 and 10, as that is the size of my grid. So my first number is 4.3, and my second is 2.1. So I'm going to find the location that these two intersect, and then I'm going to measure the depth. So my location is here. I'm going to use a piece of equipment called an auger. It's got this thread on the end which helps me to screw it into the ground. But you could use a knitting needle, like this, or a barbecue skewer, or a pole if you can get it in. So I screw the auger into the ground, and I keep going until it starts scraping against the rock. Once it's scraping against the rock, I mark where it's come up to, and then I need to pull it out, being careful not to damage my back. Okay, so it's given me a sample of the soil, which might be useful, but I'm also going to measure, using a ruler, how deep that soil is. So my soil depth here is 17 centimetres, so I'll take a record of that. How many times would I need to measure? Well, that depends a little bit on the variability that I would find. I might start with 10 samples within my random area, and then I want to look at how much they vary. If they vary wildly, maybe some are 2 centimetres and some are 16, and then you've got some more that might be even a metre, then I'll need to take more measurements in order to get a reliable average. I could use a running mean for this. The final stage is then to take my depth and compare it to the tables provided by Bradley et al. So I haven't taken 10 readings or more, but my depth was 17 centimetres. So if that turned out to be the average, then I would compare that to the table. So average depth of 17. Carbon dioxide per hectare is 440 tonnes per hectare. Now a hectare is 100 metres by 100 metres, and you'll notice that it's carbon dioxide. So if we want to know carbon, we need to do a calculation to convert that. Before we move on, we need to consider the assumptions we are making again and make sure we've made a note of those in our table. So this research is based on someone else's data. So it's published in a peer-reviewed journal, so their methods are likely to be very reliable. In fact, these estimates have been used by the Intergovernmental Panel on Climate Change, the IPCC, to quantify carbon in soils. So it is well accepted data. So they are great advantages. But by using their research, we are assuming things are the same here. Even if 17 centimetres is a reliable average depth for the soil in this semi-natural pasture, what else, even within this land use, might cause the amount of carbon in the soils to differ? Okay, so the amount of carbon might differ mainly because of what's gone into it. So maybe the rock type, the organic matter, so the vegetation that's rotted down, maybe the drainage as well, how much water moves through it, transferring particles. You could investigate some of these characteristics and how they differ between soils. We could easily check the differences in rock types using geological maps, for example. We could measure infiltration rates in order to understand drainage, and the technique for this is covered in the water skills video. These things would allow us to understand the differences, and they could act as control variables. But it would be hard to get an amount of carbon for these differences. One final thing we can quantify about carbon in soil, if we have access to a furnace, is the organic carbon. So if I look closely at the soil, there's bits of stick, there's bits of roots in here, so I can assume that actually there's quite a lot of organic matter within this sample. So to take a sample of the soil itself, I could use a trowel from just under the surface of the vegetation, or even better, I could use an auger, because then I can get down deep within the soil and I could be consistent about the depth I go to, or I might even find different depths within the soil. We need to consider ethics again here. I'll have to take my soil sample away to do these measurements with the furnace, and I don't want to take so much that I'm harming the environment. Ideally, I could return the soil to the sample site at the end of my investigation, but as a minimum, I should be careful to leave the surface, the vegetation, intact as much as possible to prevent increasing erosion. With my samples, I'd then need to dry them in a 100-degree oven so that all the moisture has been removed. I need to record the weight of the dry soil, and then I need to burn it at 450 degrees. That's why we need a furnace. Your house oven won't go to that temperature. So if you have a school furnace in the science lab, for example, you might be able to use that. Once I've burned my soil in the oven at 450 degrees, I then need to weigh it again. And then the weight difference between the dry soil and the burned soil is the amount of organic carbon. So we're now at the peat bog on Brund Fell. This is an area of really thick organic vegetation which hasn't rotted down. It's anaerobic, so there's no oxygen which prevents it rotting. It's a very wet and boggy environment, and it's sort of kept within this area by the hillside around it, so it's quite rocky around, and we've almost got like a basin underneath. So this is the peat bog. And like vegetation in trees and soils, we can estimate the amount of carbon in peat if we know what volume of peat we have. So GCSE maths again, volume is area times depth. So to work out the surface area here, we could use online mapping, such as ArcGIS, to draw around the area of peat, and that will tell us the size of the area we have drawn. But peat is a lot deeper than soil, so we can't use an auger or a knitting needle to work out the depth. So have a think about what type of sampling we could use to work out the average of depth of peat across this area. We might do random sampling like in the woodland, but because peat usually accumulates in a basin, we probably expect it to be deepest in the middle and shallower in the outsides. And so to get an overall picture, we might need to sample systematically across the basin. So if the area is 50 by 50 metres, for example, we might measure the depth at 10-metre intervals across the length and width of the basin. So peat is a lot deeper than other soils, so we can't use the auger or the knitting needle as we did before. So I've got some threaded bar, which you just buy from a DIY store, and the nuts on the end secure them together. So I'm going to push this one in a certain way. This one's they're all a metre long, so I can measure them as they go in. And then I'm going to attach this one to the other, making sure it's nicely secured so I don't lose my pole inside the bog. And then once it's secured, I'm just going to keep pushing it in. So it's down to a metre, and I'm at the bedrock there. So I'm going to work out where the pole comes to, and then I'm going to pull it back out. Once I've pulled it out, I'm going to measure this bit using a tape measure, and and I know the bit at the bottom was 1 metre deep.
So we've measured the depth of the peat. In order to get a volume, we also need to know the area it covers. So I'm using ArcGIS here. It's got some aerial imagery, and on that aerial image of my location, the darker area in the middle of this circle is the peat bog. I can use the measurement tool in order to work out how much the area of peat is, and I draw around it and it gives me the measurement in square kilometres, so that's 0.03 square kilometres or 30,000 metres squared. So to work that out into a volume, I take my average depth, which across the whole of this peat bog is 2.8, and multiply those together. So the volume is 84,000 cubic metres of peat in that one small peat bog. To get that into biomass, a little bit different to what we did with the soil and with the vegetation, I'm going to times it by 0.15 because peat is approximately 85% water, so that'll give me the solid mass. So that gives me 12,600 tonnes. We already know that biomass, to get biomass into carbon, we need to halve it. So the carbon is 6,300 tonnes.